spent quite a lot of time, in fact all the time so far in the course, talking about what are known as memoryless circuits. Okay, that is, we have studied circuits with independent sources, resistors and other linear elements like control sources. What is meant by memoryless is that the solution at any time depends only on the input at that particular time. Okay, we didn't consider time varying signals at all, right? In every problem that I gave, the inputs were fixed or DC, that is constant with time. But if I simply changed it as a function of time, all you have to do is, everything was simply proportional, right? All our solutions, and let's say we have some Vs as the source, all of these would be of the form something times Vs. Now, if this was a function of time, all that would happen is that would appear here, that's all, right? So, there is no memory in the circuit. The solution at any instant depends only on the inputs at that particular instant. Okay. This is what we have solved so far. So, we had voltage and current sources and R and control sources, which are also just linear control sources. Okay. Now, it is useful to go through this. Of course, we have looked at systematic methods of circuit analysis and so on from this one. All the nodal analysis, mesh analysis we considered for this type of network, right? Because everything had only either voltage or current sources and resistors. Okay. But this is not complete. What is missing from our selection of components here? Yeah, capacitors and inductors. I mean, you are of course familiar with them. They are common components, so presumably they are used somewhere. Okay. So the techniques that we have used so far cannot handle capacitors and inductors, right? And so what we will do here onwards is to look at how to analyze circuits with capacitors and inductors. Okay. Capacitors, inductors, mutual inductors, all those things will be similar. So these circuits, these elements L and C have memory. In what sense do they have any memory? So what will be, if you take a capacitor, what will be the voltage across it at any given time? Huh? Yeah, so it's basically the charge on the capacitor divided by the capacitance, and the charge itself is the accumulation of all of the current that has flown into the capacitor from t equal to minus infinity to now. Okay. So clearly the present state of the capacitor depends on what happened in the past, how much current flowed in the past. Exactly the same with what? Inductor. So what does it store? What does it store? A capacitor stores charge. What does an inductor store? Yeah, flux or flux linkage, I guess, to be more precise. So what is the voltage across an inductor? L di by dt. So what does it, I mean, what is it memorizing? The current in an inductor depends on the voltage up to that point, right? So basically it's related to the integral of the voltage all the way from t equals minus infinity to then. Okay? This is fine. So that's how these two elements bring in memory into the circuit. Okay. So obviously these, I mean, the interesting difference between the circuits earlier and this is when you consider time varying inputs. Okay. If you have a constant input also it is interesting, but we will see that time varying inputs make it even more difficult. Okay. And certainly actually it becomes a lot more difficult to analyze time varying inputs with capacitors and inductors. You certainly can't analyze it with a fixed voltage, and if now that has a time dependence, simply throw the time dependence on the solution. That is not how it works. Okay. And again, as with the other circuits that we analyze, you know some of the initial analysis of this. We will go through that, but we will go slowly and then make sure that you have a way of systematically analyzing any circuit consisting of L's and C's and resistors and control sources and so on. Okay. What is the voltage here? What's the voltage? It's the resistive divider. Now, if I have a circuit like this, what's the voltage here? Huh? Vs. Why? How will you find out? Finally, initially. So, how did you find this solution? I mean, besides, of course, you remembered it and it's a really simple circuit. How do you find that? So, you imagine that this is some voltage, let's say Vx. First, you write KCL, Vx by R1 equals the current flowing from there, Vs minus Vx by R. Okay, and you solve for this. So, what should you do in this case? So, let's say this voltage is Vc. You have to again do the same thing. You write Kirchhoff's current law. So, what is the current flowing through the capacitor? It's capacitor, capacitance times the time derivative of Vc, C times dVc by dt, and that will be equal to what? Vs minus Vc by R. Okay. Is this fine? So, the main difference is that in this case you would you have an algebraic equation, and in fact any circuit of this type, any number of resistors, any number of sources, you will have only an algebraic equation. That is what makes it easier, whereas here you have a differential equation. Okay. So, again you know the basics of solving differential equations. In fact, probably you know more differential equations than what is required in this particular course, but we will go through it slowly nonetheless, just to make sure that because the main point is not just to be able to solve it, but to get some insights into the circuit as well. Okay. So, let me rearrange this so that as usual all the variables are on the left hand side and the inputs are on the right hand side. So, if I do that, I would get okay. Alternatively, it could also be written as okay. Any questions so far? So, this is what we have to solve. I mean, in general, everything will end up with some differential equation which you have to solve. Now, whenever you have a memory element, you have to specify its state. Okay. So, let us say I will say that I will give you whatever Vs is. I mean, Vs may be dependent on time. I am not showing that here, but whatever Vs is given, and I ask you for Vc. I know it could be time dependent probably. I know I want to know it for t greater than 0. Okay. Now, I do not solve everything from t equals minus infinity, right. So, then whenever you have these memory elements, you also have to specify the initial state of the memory element. Okay. Because obviously, I am looking for solution at some time onwards. So, you should know what happened before that, or rather you do not need to know the details of what happened before that. All you need to know is the state that the capacitor was in. Okay. So, and of course, when you study differential equations, you also know that you need the initial condition to be able to solve for the differential equation. Okay. And what is it? What is the state of a capacitor? What will you specify? The voltage across it. Actually, it is a charge, but we deal with only voltages and currents, and we know that voltage is linearly related to charge. So, its voltage, because this is what depends on the history, right? The voltage of a capacitor depends on all the current that has flown in the past. So, if you specify at let us say t equal to 0, you do not have to worry about what happened in the past. You know that its net effect has been to put let us say 1 volt across the capacitor. Similarly, the same for an inductor. You do not need to know the voltage from t equals minus infinity to now, right. All you need is the current at t equal to 0, or whenever you want to start solving the problem. Okay. So, these two also have to be specified. Okay. Now, let us say we go progressively to more complicated inputs. We will first solve for Vs being a constant and then time varying. Again, for arbitrary time varying circuits, arbitrary time varying inputs, it may be difficult to write the answer. For this circuit, it can surely be done, but in general, it may be a little more difficult. So, we will consider some kinds of time variations which are particularly interesting. Okay. So, let us start with Vs being a constant, and I want to know the same thing, Vc of t for t greater than or equal to 0. So, because I asked you this, I will also have to tell you how much the voltage across the capacitor is at 0, or to be technical, you want it for greater than or equal to 0, I need to specify for the instant just before 0. Okay, that is what is denoted by the 0 minus, right. Let us say that is 0 volts. Okay. So, what will happen to Vc? What do you guess will be Vc of t for t greater than or equal to 0? What will happen? What happens just after t equal to 0? What happens? What is that? Start charging. Why? Yeah, why will it flow? Let us stay with voltages and currents here, right? So, where? How much current will flow through the capacitor? It is whatever is flowing in the resistor, right? So, and what is the just after t equal to 0, what is the current in the resistor? Vs by R. Okay. So, just after t equal to 0, a certain current starts flowing because the resistor has some voltage across it. So, it has to have a current, and here this current has nowhere to go, it will go into the capacitor. Now, as it goes into the capacitor, what happens? A capacitor will start charging at what rate? What will be the rate of charging? You understand what is the question? What is the rate of charging? Huh? Current, yeah. So what is it? Vs by R. I am looking at the capacitor voltage. So what should be the units of rate of charging it? dV by dt. Okay, so give me some answer that has the dimension. That is what I want to know is what is the value of dVc by dt? I by what is that? I by C, Vs by Rc, right? Vs by R is the current flowing. So what happens is that at t equal to 0, I mean if I just draw it, it will start increasing, and what will be the slope of this? The current is Vs by R. The current here is Vs by R, right? The current through the capacitor is Vs by R, and that has to be C times the time derivative of the voltage. So the time derivative of the voltage is the current divided by C, obviously. So it will start charging. So what happens if as it starts charging? Huh? Yeah, and then first of all, don't say current across. Current is always through. Okay. We have a two-terminal element. Current is through the element. Voltage is across the element. Okay. So what happens as the voltage on the capacitor grows? The voltage across the resistor decreases, right? So the current will decrease. So what? Yeah. So actually it doesn't go up like that. The moment it has gone a little bit, slope will reduce, and then it will reduce further. Okay, it will reduce further and so on. Eventually what happens? The slope becomes very small, but actually never 0 until t equal to infinity. You know the solution to this already, but we are looking at specific things, right, like circuits. So you need to understand what's going on in terms of the electrical variables. So here what is happening, of course, is that initially you have a certain amount of charging current, and it will start charging it, but as it is charging, it affects the charging current itself, and in this case the current goes on reducing. So the voltage across the capacitor starts changing more and more slowly, and eventually it will become nearly flat but never quite so. Okay, that we will see from the solution, but that you see from this picture as well, right? This is okay? So this shape, I think you know the solution already, so that will come out to be an exponential, but this is what happens. So let's say Vs was 1 volt, and the initial state of the capacitor was 2 volts. What would happen then? Vs is 1 volt. I had already solved it for, or at least sketched the solution for the case where the initial condition is 0. But let's say the initial condition happened to be 2 volts. So what will? Why? What happens in the circuit? Just again look at the voltages and currents and tell me. What is that? So initially if you have 2 volts here and 1 volt here, what happens to the resistor? It will actually have a current in that direction, right? 1 volt divided by R. So it is drawing current out of the capacitor. So obviously the capacitor voltage reduces. So you start with, let's say, 2 volts. It reduces. What is the rate at which it will reduce? What is the rate? Watt by R. What will be the slope? So it is 2 volts minus 1 volt divided by R. That is the current. That divided by C is the slope. Okay. So minus 1 volt by RC. But as it falls, what happens is this voltage reduces. The current again reduces. So it becomes shallower and shallower and shallower, and eventually come very close to 1 volt, but not quite 1 volt. Okay. So, I mean, this is quite simple, but like I said, let's go slowly and then understand what's happening in the circuit. In fact, it turns out this is exactly what happens in every circuit of this type. If you have a single capacitor or an inductor, what are known as first order circuits, as we will see later. Okay. So, now let us say instead of the current, I mean my problem asks me for, instead of the voltage across the capacitor, the problem asks me for the current through the resistor. Okay. So, the initial condition is 0 and Vs is 1 volt. Okay. How will you solve for this? What will this be? Yeah, again look at the circuit and tell me what happens to the current. Obviously, we had if you have the expression for the capacitor voltage, you can find the current, I know, by Kirchhoff's law or simply by the capacitor characteristic. But now look at the circuit and tell me what is happening. What is the resistor current immediately after? Huh? Vs by R or 1 volt by R. And after that, it will decrease. Yeah, it will go on decreasing because the voltage across the resistor goes on decreasing and it will do that. Okay. And from some other initial condition, again you can figure out. Okay. So, this is how, I mean, this is the general nature of solution to any differential equation. Depending on the initial condition, you start somewhere and then you eventually reach some other place. Okay. Now, one of the things that you see from both of these is that regardless of where you start, you will eventually end up in the same place. Okay. This is true of all the circuits that, or most of the circuits that we will consider. Okay. These are known as stable circuits. So, you have, regardless of what initial condition you have, the initial condition surely influences the solution. Okay. But if you wait sufficiently long, whatever remains after that will not depend on the initial condition. Okay. So, these are known as stable solutions. So, actually there are two parts to solving for circuits like this, the part that depends on the initial condition and the part that depends only on the input. Okay. So, those are known as transient and steady state solutions, and we will look at those things as well. Okay. So, every circuit with capacitors and inductors will have memory elements will have these properties. Okay. Depending on the initial memory, it will have something, and then finally the effect of memory will die away, just like you have forgotten what I taught in the first week. So, you will only react to what is happening right now. Okay. So, it will only depend on the inputs that are applied. Okay. Any questions about this? But one of the important things is, I mean, again, the differential equations that we solve, this will be done in like maybe 5 minutes in a maths class, right? Because we will look at the first and second order differential equations with constant coefficients. That is pretty much what we are going to look at here, and that is really not interesting for a mathematics class. But here, solving it is one thing when posed as a differential equation, but you also need to know like what's happening in the circuit. So, that is why you should also develop some reasoning by looking at the circuit, exactly what happens and so on. Okay. So, let us go back to this. And the differential equation that governs Vc. By the way, I mean, just like you can choose variables for circuit analysis, you can choose any variable, right? Currents or voltages or some combination. The same thing is true here also. Now this circuit is so simple that I will take something as variable without like formally going through nodal or mesh analysis methods. But and I will write the differential equation in terms of this voltage, but I could equally well do it in terms of the current through the resistor or capacitor or anything else in the circuit. Okay. So we saw that this is the differential equation governing the circuit, and I will assume now Vs is a constant with time. Okay. So what is the solution to this? Basically, Vs is a constant with time. Of course, Vc is not. So what will be the solution Vc? Huh? What kind of function is? I can't hear. Yeah, so that is the particular solution. What will be the form of Vc? Exponential. How do you know? Why is it an exponential? Yeah, so basically you already know that it is the solution to a first order differential equation. It's actually very easy to see also for the particular case where Vs is 0, right? So in that case, or okay, so you can see that basically, I mean, Vc of t is on the right side and the derivative is on the left side. So whatever function Vc is, the derivative should be the same function. So even if you had not heard of differential equations, you could have looked at the table of derivatives. Hey, this and this, they are the same animal on the left and right hand side. So that must be the solution, right? So the exponential is the solution to the first order differential equation. Okay. So I don't have to, I think, go through this. Obviously, Vc of t is exponential. What is inside the exponential? Huh? Yeah. If you try this with something here, t times alpha, you will find that it has to be minus 1 by RC. Right? So essentially, the solution to a first order differential equation will be of the form exponential of minus t divided by some number that depends on the circuit. What is the dimension of this quantity? Time, obviously, because the argument of the exponential should be dimensionless, so that has to be time. Now, if you arrange the first order differential equation like this is the kind of classic way of doing it, variables on the left hand side and the fixed inputs on the right hand side, and you scale it so that the coefficient of the constant term, I mean coefficient of the term which doesn't have the derivative is 1, then this multiplier will be the time constant. Okay. So it's the same thing that appears here, right? But you have to be careful. I mean, don't do it with 2 here or some other number there. That is not the time constant. If you normalize things so that the coefficient of this variable term is 1, then whatever is multiplying the first order derivative term, that is the time constant. Okay. So that's basically the solution to this. And then we have to, I think you know these things from differential conditions. There are things like particular solution and the homogeneous solution and so on. So when you have 0 inputs, you will have some kind of solution that is known as the solution to the homogeneous equation. And these differential equations are also linear. So you know that any scaled homogeneous solution added to the particular solution is also a solution, right? Because the right hand side here is 0. So you know that you have to basically do some work to get the final solution, and you will get a unique solution only if you specify all the initial conditions. Okay. So again, I think you have done all of this. You have analyzed RC and RL circuits before. Where? Huh? 12th standard. Okay. So, we will do it, but we will do it in a little more detail because I mean the way it is done in 12th standard and so on may not be good enough to cover like all kinds of circuits that you would see. Okay. Anyway, you can brush these things up and we will also do it in quite a bit of detail.